Alright, so I do gotta let you guys know we've got the kitchen just over here. So there is a tiled floor, so if there's any spillage or anything like that, just be wary of that. We've also had to use 2 chairs to prop up the whiteboard, so they're sticking out from the wall, so just kind of stay over that side and it won't be a tripping hazard for you. Are you guys all cool with that?
Yep.
Yep. Awesome. So, keep that going. We're going to be learning Dijkstra. I might rewrite that. And A star, which is actually spelt with an asterisk. A star. So they're just pathfinding algorithms, and we're going to go over a demonstration that will show you guys how it works, and then a second demonstration that will show you kind of how you can apply it to like a real world situation. I can just crop all this. Oh, there's so much more space.
So much space. The 2 activities.
There you
go. Water.
Right.
Nah.
Soft drink.
Straight syrup, yes please.
Soft drink or water?
I'll take water.
Ice.
And
You started recording, yeah?
yeah,
Yeah.
I can just crop.
Yeah, it's all good. Pouring alcohol in class.
Yeah.
Step 1, get the vodka.
Welcome to Professor Jackson's class.
We're doing pathfinding today.
Stay hydrated, kids.
How you go from over here to over there?
Oh, this is my kind of class.
If you get that question wrong, you do a shot.
Yeah.
Then you realise that you're teaching health education.
No, I'm
it's pretty
teaching the dangers.
So this is what it does to your liver.
Yeah. You'll see the effects in a couple of years.
Can we just have someone upstairs at 15 minutes in, they come downstairs?
Like poke their head into frame, poke it out.
That's how I'll enter the class. Come in. Alright, guys.
Sorry, I'm late.
Thank you.
I'm going to put something in my hands, otherwise I'm going to get feeling.
Should we be writing stuff?
I didn't bring any materials for you guys to write. It's all theory, not delving into code.
Put your phones on silent, yeah? Because we're in a classroom.
I'm going to leave my phone not on silent. Should probably.
And then you can reprimand
I'm
us
gonna take
in real time. Who's got the phone
I'm
on?
gonna take it off silent for the first time in my life.
Confiscate our phone, call our parents.
Sorry.
Don't call the parents.
I need like a big 1 meter wall, bang on the table.
Actually, get a tennis ball, record the idiot ball.
Takes Ray off screen and just starts crying. I've had enough of your shit. Get out of my class.
It's just it goes silent and it's just got closed captions, gunshots.
Alright, I guess we just start, yeah? Alright, so we are going to be learning about pathfinding algorithms, and we're going to focus primarily on Dijkstra and A star. A star is written with an asterisk, but it is called A star. They're very similar. Dijkstra is kind of think of it as like an entry level to proper pathfinding, and then A star builds upon Dijkstra. So, basically, the way it works is Dijkstra is a flood algorithm. So it takes its starting position and just searches outwards until it finds the end, and then paths from there. So Dijkstra, it will always give you the quickest path. I'll show you an example. So we're here, right? Pretend that this is all like a proper grid. So like 1, 2, 3, 4. Like this would be 1, 2, 3, 4. That sort of thing. Dijkstra searches out from the start. It goes, okay, what's around me? It goes this, this, and this. It grabs all of those, and then it goes, what's around them? It goes here, here, here. This has nothing, and it goes here. And we're trying to get to here, right? That's our end position. So now we're no longer looking at these. We don't care about them. They don't have anything to do with us anymore. We're only looking at these. We know this doesn't have anything around it, so we ignore that, and we search the next few nodes around, and then we go again, and until eventually we hit that, and then we draw the quickest path, which is that. A star, on the other hand, it uses a heuristic approach. So basically, same start position we've got here, same end position, right? But A star, it does its own calculation where each node throughout the whole thing, we basically go, how far is that from our endpoint? So we still add these 4, so let's do that, right? And then we go, well, how far away from the endpoint are they? We don't know about any of the walls. None of these algorithms know about the walls predeterminedly. So we then go, okay, next plot out. Because these roughly, from this example, they're roughly the same distance. We don't care about this, even though it's got nothing around it, we don't even check if there's anything around it, because it's just in the wrong direction from E. So we then add these onto what we're looking at next. Then from there, we don't care about this one anymore. It's too far away. These ones are closer, so we see what they're doing next first. This has nothing around it, so we don't check that. We check here, and then we go, well, this is 3, and this is only 2. So on the next step, we go, well, maybe we'll check here as well. And we're here. And then we go, well, we found our path now. A star, it's much quicker, but it's also more computation heavy. So what we're doing is we're adding the distance to how many steps we're taking, and then doing a calculation to decide where we're searching next based on that number that we get. This is only something that a computer can do. There's also pathing algorithms that we human people use as well. If you think of something like a hedge maze, right? You go into the hedge maze and you can see there's a path in front of you, there's one to the left, there's one to the right. You wouldn't use any of these because these would basically require you to go one step forward, look around, go back to your original position, go to the side one, look around, and basically you have to keep all those places and only go a little bit further each time. What we tend to do is either a left first algorithm. That's, you probably heard, when you're walking through a maze, you can put your hand on the left wall and just follow that, and eventually you'll get to the end. Unless there's like an infinite loop somewhere in there, but that's when you got to use your own intuition to be like, I'm walking in circles. Or very commonly we do a depth first search. So we'll come into the maze, we'll see there's 3 directions, we'll pick one at random. If you were doing it through code, it would be predetermined based on which order you search in. But we would go, all right, let's go that way. And we walk that way until we hit a dead end. And then we turn back and we go, all right, well, that didn't work. Let's go this way instead. And we go that way until we hit a wall, that sort of thing. These basically require you to go multiple directions all at the same time. And you'll notice that Dijkstra in particular searches like this, concentric circles that get bigger and bigger and bigger. A star, on the other hand, will do one concentric circle and then it will go like this. And even though I'm like leaning over, I'm deliberately like skewing it towards the end. There's huge applications for this in video games in particular, but you can also, they use this in all walks of life. I've got another example, which I'm going to put up on the board in a second, that's based on a road map. So Google Maps actually uses A star. We're going to go through, I'm going to chuck the example up on the board, and then we're going to go through it with Dijkstra first, and then we can go through it with A star as well. And it's pretty straightforward. We're going to treat it as though we are a program. So I'm going to have on the right hand side here, we're going to have some, not code, but sort of the order that your program would look at the data in. So I've got a picture of what we're doing. It's very straightforward. This is going to simulate sort of a road. And you can also take this sort of approach in video games as well, and I'll explain how that kind of works. Okay. So I'll just show you what we've got so far. It's just a bunch of circles at the moment, but we'll connect all the lines together. We're basically creating a map of where it's possible for us to go, so that we can then calculate which path is the quickest. And you'll see as we're going, oh, sorry, that goes there and there, yeah, there. Cool, so, quick update. We now have a little map, and basically these lines just tell us where we can go, right? You can't go straight from here to here, you have to take one of the paths. That's what we're working with. And this is, you can think of this like a road map if you think of this as sort of Melbourne, right? You've got your Melbourne Central, you've got Flinders, you've got Southern Cross, you've got Parliament, and just random nodes in between. So, the way that we can apply this to games is sort of think of these as locations that can be like towns, for instance. So we are going to have, our start position is going to be up here, and our end position is going to be here. I'm doing an X because we're going to put letters throughout. I don't want two E's. Let's just add those. A, B, C. Doesn't matter where these are. Obviously, this is an example. G, H, I, J. Alright. So if you think of it as, let's do it as a video game, right? So you've got your starting location, and you want to go, if you were to go over here, this has a cost of 3. Now that might be distance, it might be terrain, it could be anything. What matters is the cost to go from here to there is 3, right? And then you've got from S to B, that's 7. And that could be, like, even though it looks shorter to us, it could mean there's a swamp there. It takes more effort to get through. So I'll chuck all those numbers up now, but basically these numbers represent the effort it takes to go from node to node. So we've got 2, 3, 4, 4, 2, 3, 1. And these, even though I'm reading them off a thing, they are random. I actually don't know what the optimal path is. That's okay. We have pathfinding algorithms. And then 2 and 2. Yeah. So we can tell, because we have eyes and we can see the whole map at once, we can tell that ignoring the numbers, that's the shortest path. Right? If we were to use a bit more intuition, we could probably see, well, if we divert to A and then B, we skip this 7, that's only 5, it's shorter, so we go like that. But we can see the whole map. We know that over here there's a 6, so you ignore this. Like, you would never even check this, because A, why would you ever need to go there for extra cost, and B, it costs 6. 6 is really expensive in this chart that we're using at the moment. So, how do we do it? Basically, Dijkstra, we start at S and we go A, B, C, all at the same time, but we have to do them individually. So I'll jump on that side, and hopefully, I should still be in frame. So, am I still in frame? Cool. Alright, so we put S is here, right? It has a cost of 0. It doesn't really matter because it's our starting position. So now we go A, and we put that here, and we put a little S next to it so that we know when we're talking about A, we're talking about it in terms of coming from S. Because there are points where you look at A as coming from B, that sort of thing. So that has a cost of 2, right? Now we look at B. We go B as coming from S, has a cost of 7, and then you've got C, as it comes from S, has a cost of 3. This. Okay. So basically, we grab our 3 nodes and we go, what's cheapest? A is cheapest, then C, then B. So we get rid of B and C, and we swap them around. We basically order it based on the cost. Alright, so C as coming from S, B as coming from S, and that was 3 and 7. Alright, so now we expand upon that. We take A off the top here. We're now looking at A specifically. So we put A over here. That's coming from S. And we go, well, A can also go to B. So let's look at that. Let's go B as coming from A has a cost of, from S, has a cost of 2 plus 3, 5. Right, so that's already cheaper than B coming from S. Where am I? Alright, so now we look at D. We have D as coming from A, has a cost of 2 plus 4, 6. And now that we've done that, we reorder it again. So the computer obviously does it a bit quicker than us because we're people. But we can see C is next, then B, then D, then B from S. So let me reorder it without wiping it out so that I don't forget the order. So we go, this is now the order that we're going to check next. Why did I write A? B as coming from A, has a cost of 5. D as coming from A, has a cost of 6. And then B coming from S has a cost of 7. We know now that we have a B higher up in the stack, so we can ignore this one completely. We no longer ever consider B as coming from S. It might as well not exist for us. Alright, so it does take a while. The computer obviously does all this in, well, there's what, how many nodes? Up to K. It does it in about 20 frames. Like that. Quicker than you can think, I might do a pathfinding. It has already done the pathfinding. Alright, so let's grab C. We'll put C over here for now. C is coming from S. And we keep those, sorry. So C has F. So we got F as coming from C. F is 2 plus 5, 2 plus 3, 5. And that's the only node coming from C. So we just add it to the stack. Now, the way that this is interpreted in code is that you add that on top. So F would be here. Because when you're thinking of a, so it gets put into an array, right? The way you can think of an array is like a tennis ball tube, right? You got all your numbers, as you put them in, they're at the bottom of the tube. You can't just grab the one at the bottom, you have to take them all out one by one. So the last one you put in is the first one you take out. So we've just put in F, so we now search F before we search B. We know, looking at it, that B is going to be better because there's a 1. The computer doesn't know that in advance. So let's wipe that off. Let's grab the F from our list, and we'll put it over here. So it's F as coming from C. So F then looks at G as coming from F, and H as coming from F. Both of them have a cost of 4, so it's 4 plus 2, 6 plus 3, 9. They both have a cost of 9, right? They both then get added because they're the only 2 coming from F. We ignore C. We've already seen C. We already know about C. So we add these to our list. They're both higher than 6, so they go below because after we reorder it. So we've got G as coming from F and H as coming from F, both with a cost of 9. So we're now back over at B as coming from A. So we've got this. This is our path so far. So it's, sorry, I didn't mean to throw that there. Let's get rid of B. We'll look at it over here. These also get cleared off as we're going. I just forgot to do that. So I'm just going to leave them there as these are the ones we've been actively looking at, sort of thing. So we've got B as from A. We're now looking at D and E. We've already seen D. We've already got D here. That's fine. We have multiple Ds. So let's do D first. D as coming from B has coming from B, but we know that the B comes from A. That's what we're looking at. So we don't count as 7. So we count from D. We go 4 plus 3 is 7 plus 2 is 9. Right? And then E, we do the same thing as coming from B. We go 1 plus 3 plus 2, 6. So that's starting to look pretty good. We will add D coming from B to our stack at the bottom because it's 9. And we add the E at the top because they're both 6. D coming from A and E coming from B are both 6. And we learned earlier, we check E first because it's the last one we put on. You can run into funny things if you're putting it into the list and then reordering it every time. But if you don't need to reorder it, you shouldn't be, basically. So let's look at E from B. I don't even know what happened there. My brain just turned off for a second as I started writing. Sorry about that. E is coming from B. Rub that off. Yeah. So we now we look at K and we look at J. We know K, that it's stupid to even look. Computer doesn't know that. Computer just sees there's a node going there, so we have to check it, right? This is where the difference between A star and Dijkstra comes into play. Because A star would never check K. K coming from E. We've got 3 plus 1 plus 3 plus 2, 9. And then you've got J as coming from E, which has a cost of 2 plus 1 plus 3 plus 2, 8. Alright, so, I almost rubbed them off. Let's add them to the stack. So let's chuck K at the bottom, coming from E, and we've got this D as from A, but we can ignore that now. No, we do have to check it, sorry. So that's what we're checking next. So let's put it here. Because we don't have D anywhere, we still need to check, is there a better path? Because we know, but the computer doesn't know, there might be a path that goes from here straight to there that only costs 1. And that's suddenly the cheapest, right? We know that there isn't. We know we've already checked everything around D, but we haven't actually checked it in code yet. So let's get rid of that. We'll add the J, which is now 8, which is our best. And that was a 9. Let's rub those out. And we're checking D, but we don't have to write anything. We've checked everything already. We've said, sorry, no, we haven't checked K yet. We know about K, we haven't actually checked it. So we do need to check it. So K as coming from D has a cost of, where's D come from? D's come from A. So it has a cost of 2 plus 4, 6, plus 2, 8. And unfortunately, that puts it at the top of our list, which I'm not going to move stuff around because we already know what's connected to it. But basically, it would then grab K and go, what's K connected to? It goes, oh, it's only connected to D and E, both of which are already in our list. So we get rid of that. I will write it here so you can see what is actually being checked. We're up to J now. And we know J is the end, but let's do it anyway. So X is equal to 2 plus 2 plus 1 plus 3 plus 2, which is 9. And we found our path. So we then go backwards, right? So to make our actual path, sorry, before we get to that, we know this is a cost of 9. The computer will still check these. It will basically open them up, and if there's a cost of 0, we're good. But because they're the same number, as soon as any of these numbers get higher than that, it'll discount it. So we're just going to discount it now rather than waste time going through it, because none of our costs are 0 and they're already at 9. So they physically can't move while still being the same number or cheaper. So let's get rid of that. So, sorry, that should be x as from j. So we know our path is x from j. So we go x, which is then j. Where was j? I didn't write j. That's my bad. J from e. We go e. Where was e? E's up here. E from b. Where was b? B's up here. B from a. And then a to s. And that is the shortest path, cost-wise, from Dijkstra. That will always give you the shortest path because it checks that number. And in terms of a game, you actually want to invert this because, like I said before, it's like a tennis ball in a tennis canister. Think of this box I drew out as the canister. S is at the bottom. We need S to move. That's our starting point, right? So you would just invert the list and basically flip it around, and then if you want to move, you go S to A to B to E, blah, blah, blah. Now, there's a lot of other things as well. With code in particular, if you think of these numbers as specifically as terrain types, right? Like a 7 is a swamp, right? But we have a swamp demon monster who gets a speed buff. So that 1 for a swamp that 7 for a swamp might be a 1 for him, which would change the path for him, which doesn't get used enough in video games, in my opinion. You could have 10 units that all have different pathing. Like you think of Age of Empires style, right? You grab all your units and you say go over there. And they could all split off in different directions to take their own quickest path. Which I think is really cool, but it never gets used. Alright. So let's run that off. Alright. I did forget to ask, do you have a tape measure by chance?
I do.
You do?
You need it now?
Yeah. Yeah. This part will cut out.
I was
Break time.
gonna say walk off screen back.
Where's my drink?
Yeah, as
Did you have a question, Ray?
Yeah, in regards to this is very particular, but it can be applied to any form of grid-based mechanics as well. So, like in a sense, a chessboard can it be applied to
Yes.
something?
Yeah, 100% can be. You would just basically place the nodes in a grid pattern. This you can think, like I mentioned before, you can think of this as like Melbourne, for example. But 100% you can have it as a checkerboard or any amount really. I mean, if you wanted to, you could have every node connecting to, I was going to draw lines there, to every single node, right? So even like through there, through here, and they all just have different costs. You can get from anywhere to anywhere in one movement, but it costs a lot depending on your situation. In terms of pathfinding, you generally wouldn't look very far. It makes, I suppose it would make the movement really interesting because you could have S to G cost 1, right? And then G to A costs 1. And you might have a convoluted path that gets you from S to X all costing 1. And you end up making 15 moves where you could just make one move, but that one move costs 20. So it could be more efficient to make 15 moves. Right, so tape measure. Let's do A star. So the tape measure we're going to use as, sorry about that. Basically, when A star does its check of how close a node is, it's using what's called the Manhattan formula. I don't know why it's called that because it's just Pythagoras theorem. It draws a triangle from the start to the end, from the node to the end. It just goes down, down, and just calculates distance and then a squared plus b squared is c squared, and gets the distance. We're going to be using a tape measure because it's the best I can do basically. So we're going from x to all of these nodes. It's pretty quick. We're not going to do, like, this is in millimeters. I'm not going to write 637 because we have to actually use these numbers. I'm going to round up. So basically, give me red actually, stand out a bit more. We go from here, let's call that 15. Let's call that 34. I'm hating these numbers already. 33. 44. I might need a calculator for when I'm actually doing this. This all gets done internally and damn near instantaneously by the computer. Obviously we can't do that. 51, let's call that 61. Sorry. So the camera will not be able to see for a second, and neither will you guys. 23, 35. And last one, we'll just call that 50. Alright. I didn't miss any. No. Cool. So each one of the nodes now has a unique number. A unique number is just the distance. So A star will go through exactly the same way, right? Just because we've started our cells up in the corner, it's going to initially start off the same. So I'm not going to go through in as much detail as the Dijkstra because it's doing the same thing. Basically what you need to know is that number that we were using to add these, we also add the cost of the node itself, basically. So let me grab my calculator because I use big numbers. Right. So start at S. S is always 0 because S is our starting position. Doesn't cost anything to move to there because we're already there. So we've got S. Cost of 0. Now we're going to check SA, SB, and SC. So that's a name. So SA, you know, is 2 plus 61, 63. And these numbers, obviously, they get much bigger. They would not if I used normal numbers, but I did not. I used specific numbers. B from S, I've written those numbers in reverse. Let me do those letters in reverse, sorry. 58 and 53. Sorry, let me fix that. That must be confusing for all involved. A from S, B from S, and C from S. Right, so we know C from S is our cheapest, whereas already we've seen a change, right? Dijkstra last time had A as our first point of check-in, but because of the cost of the nodes themselves, S is actually closer to X, C is closer to X than A is, so we check C first, because we assume that we're heading in the right direction. So, let's do the same thing we did last time. Let's write them down here in the correct order. So we've got C, then B, then A. Where A last time was our cheapest path and the first thing we checked, it's now our most expensive. Because even though we know the correct path, the path itself hasn't changed. That shouldn't have changed. Might have changed. Ideally, this is still our best path, right? That might change with the numbers just because I've been pretty vague because I'm holding it and stuff. But that should still be the quickest path. But because of how these numbers work, we're now checking A last. right? So let's check C first. Now checking F as from C. We'll put C, S over here, remove it from here. Now we add them up the same way. We still include this 50, so it's 53, 55 plus 43. 98. Yeah. I can. So it's the only node that comes from C. Add it to the bottom of the list because it's got the highest number. And we get rid of that. And we go through and we do B now. So we check A as from B, D as from B, and E as from B. Right? Remembering that we're checking this number, we're not, like we're going this way. So A as from B is 61 plus 3, 64, plus 51 is 105, plus 7 is 100 and numbers, 12. Plus 61 is 173. D as from B is going to be 44 plus 4, 48, plus 51 is 99, plus 7 is 106, plus 61 is 167. Yeah, I feel like I did that right. E, 34 plus 1, 35, plus 51 is 86, plus 7 is 93, plus 61 is 154. Alright, so we add these down to the bottom of our list now. Let me drop down. We order them first and then add them. So we do E as from B with 154. D as from B with 167. And A as from B with 173. Right. And that's B done. Right? I forgot to rub it off. That's why I'm hesitating. I forgot to rub it off from here. Right, let's rub these off. Let's check A now. So A as from S, we're looking at B from A and D from A. Alright. B from A is 51 plus 3, 54 plus 61 is 105 plus 207 plus 60 is 167. Same number as D from B, coincidentally. D from A should be cheaper. Potentially, might be the same. Let's find out. 44 plus 4, 48, but can't be bothered. Plus 61, plus 2, plus 61, 172. Right. So we can add those to the list. I have to rewrite the list because we're at the bottom. Let me switch colors actually, so I can see what I've got. I'm just seeing so the camera can still see. We've got A from S, F from C. Where are these going? E from B. And then we already have, sorry, you guys can see as well. We already have B from D with 167, same as A, but that's going in new, so that goes first. So B from A, D from B. D from A is 1 point shorter than A from B. Right, Let me quickly jot the numbers down. 98, 154. I can rub these out now. Pretend it didn't happen. Up here, B from A, 167. B from D from B, 167. D from A is 172. And A from B is 173. Right, I'm going to get rid of the rest of those. So A star is, if you've got a grid like this, you're probably better off using Dijkstra because it's very small, right? The bigger the grid is, the better A star becomes because this, it's not the end of the world if you check every single node, right? Because there's not very many nodes. If you've got a grid, so I said this was Melbourne, right? Picture this, the actual size of Melbourne where every one of these nodes is an intersection. We're talking thousands, right? You don't want to check every single intersection. You want to only check the ones going in the right direction. That's where it kind of becomes better to use A star when it becomes very computation heavy. So let's check A from S. Or did we just do that? No, we didn't. Sorry. A from S. So B as from A. No, we did do that. That's here. Sorry. I didn't rub it off. It's an F. And that was 98. Right. So we're over here now. F from C is now our lowest number, so it's the one we check first. So we go G and H, both coming from F. And I'm just going to use calculator because it's much quicker. 35 plus 4 plus 43 plus 2 plus 50 plus 3 plus 61. 198. Now, H is, we can tell by looking at it, it's 1 point different. So we're just going to 197. Because they both have a path of 4 and then the rest of the path is exactly the same. They just have, H is 1 point closer than G is. So we add them down there. Luckily they both just go to the bottom. So we reorder them. So we got H, then G, as coming from F for both. Cost of 197 and then 198 respectively. Cool. And we write F off. Right, here's where we should be seeing more things than Dijkstra. We should be seeing less things than Dijkstra, sorry. We're at E now, right? So, yeah, sorry. My brain turned off for a second there. Let's wipe these off. I saw these numbers, I'm like, why are they still there? Alright, let's check E. So we've got K and J. As from E, let's get a calculator again. So J is only worth 15. J is super cheap. Plus 2 plus 34 plus 1 plus 51 plus 3, right? That is still our cheapest way. Yes. 3 plus 61 plus 2 plus 61, 230. Yep. I don't know why I did J first, but I did. And we'll grab K as well, which is 33 plus 3 plus 34 plus 1 plus 51 plus 3 plus 61 plus 2 plus 61. 249. So we know, looking in advance, because J is a smaller number than K, we know we're never checking K. Right? So we've already saved information there. We will have to go through all of these. I think we can skip that for now because it's just the same thing over and over to get to this same point. But basically, and that's only happened because of the numbers that I've used, that we're checking these at all. If it was done properly, with like exact measurements and stuff, this wouldn't be getting checked either. So I should use small numbers because we have small numbers for our path, so it's throwing it off much more. But basically, you can already see from this, we don't even look at K. We would have looked at D here, and again, no, that's because of our numbers. We should have only checked D, but we should never have actually gone into D to look at K. That's my bad with my numbers, but we know, like, let's skip ahead. We'll do J. We'll pretend we've already done all this because it's just the same thing that I've been doing for the last 20 minutes. So let's get rid of that, and we'll do J, and then we can write our order. So J to X. I've actually rubbed off the order, but we already know what it is. Is X doesn't have a cost, so 2 plus 15 plus, it's just 2 plus J, isn't it? Which is 232. And then we write our path back. So our path would be X, J, E, B, A, S. Again, to actually use it in code, flip it over. Unless, like, there are times where you want to use it in this way. It's honestly depending entirely on what you're doing. But I hope that made sense. I did kind of mess up the demonstration a little bit with the numbers, but basically, A star, it's exactly the same as Dijkstra in the way that it uses the information. It just has a bit more information, and it orders everything in the same way that Dijkstra does. Just because we're using the heuristic value of how far away is our node. Like if we had a node up here, that's obviously super far from here. So basically, A star wouldn't even consider this an option until we were like here. And then it would go, well, we've made it to here and it's been this expensive. Maybe it's not working. Let's check the other way as well, just to double check. Which is how you end up with a, rather than a cone of we check this way, you end up with a oval of also checking a little bit behind, but not a circle like Dijkstra. Dijkstra can be very powerful, can be very quick. A star in many situations is actually slower because it's doing so many more calculations. It takes more to set up as well, as because everything needs a heuristic value. And you've got to do that yourself in code. The A star algorithm doesn't do that, it just uses that information. So if you're looking to set up something really quick, but it still works and will still always give you the shortest path, Dijkstra is probably the way to go. If you need something more complex, if you're using a more complex node map, if you've got a lot of things going on at once, A star can be better. But yeah, I hope you guys enjoyed. I hope you learned something, and yeah, thank you. Turning off the wrong button. I know.